Tonight, we are going to look at something so large that every galaxy you have ever heard of, every cluster, every supercluster, is nothing more than a footnote inside it. A structure so immense that the word structure barely applies. Something that stretches across a region of the universe so vast, it takes light itself over 1.5 billion years just to cross it. And here's what makes this unlike anything else we've ever found. The largest structure ever discovered isn't a star, isn't a galaxy, isn't even a cluster of galaxies. It's a kind of architecture built by the universe itself over billions of years, out of matter and gravity and time. And by the end of tonight, you're going to understand what it actually means for something that large to exist, and what it says about the universe we're living in. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Most people have a mental model of how the universe is organized. Planets orbit stars. Stars gather into galaxies. Galaxies cluster together. Clusters group into superclusters. It feels like a clean hierarchy, each level neatly containing the one below it. And for a long time, that model held. Astronomers mapped galaxy after galaxy, cluster after cluster, and the picture that emerged was a universe arranged in what they called the cosmic web. Filaments of matter stretching across vast distances, connecting dense knots of galaxies, with enormous voids of near-empty space in between. It looked like a three-dimensional spider's web, intricate and beautiful and surprisingly organized. The discovery of that web in the 1980s was one of the most important moments in modern cosmology. Astronomers had expected the universe to look more or less uniform on large scales. Scattered galaxies, maybe some clustering here and there. What they found instead was a universe with genuine large-scale architecture, organized structure, pattern. And that discovery came with a question nobody could quite put to rest. How big can these things get? It turned out that question had an answer none of them were ready for. The first hints came with early galaxy surveys. The CFA Great Wall, announced in 1989, was a sheet of galaxies roughly 500 million light-years long. That was shocking at the time. Astronomers had expected the universe to be structureless on that scale. Lines. Instead, here was a coherent formation, stretching halfway across the field of any single major survey of the era. Then, in 2003, the Sloan Great Wall was discovered, stretching about 1.37 billion light-years across. Each new discovery pushed the scale of known structures further. Each time, there was a quiet, unsettling feeling that maybe the universe was not behaving quite the way the models said it should. Because there is a rule in cosmology, a hard-edged theoretical expectation about how large any structure should be able to get, and the structures being found were approaching that limit. What came next would push past it entirely. To understand why that matters, you need to understand something about the very beginning of the universe. In the first fraction of a second after the Big Bang, the universe was an extraordinarily hot and dense plasma, a churning sea of energy and fundamental particles in which no structure of any kind existed. No atoms, no molecules, no stars, no galaxies, nothing organized at all. Just raw energy and the fundamental particles that energy was constantly producing and annihilating. As the universe expanded, it cooled. And as it cooled, the physics changed. Around 380,000 years after the Big Bang, the temperature dropped to about 3,000 Kelvin. At that temperature, electrons could be captured by protons. Neutral hydrogen formed for the first time. Before that moment, the universe was opaque. Photons, particles of light, were constantly scattering off the free electrons, filling the plasma. They could not travel far. The universe was like a fog, so thick that light could not penetrate it. But when the electrons were captured into atoms, the fog lifted. The photons were suddenly free to travel, and they did. They have been traveling ever since. We detect them today as the cosmic microwave background, a faint glow of microwave radiation filling the entire sky in every direction. It is the afterglow of that transition moment, frozen in time, carrying information about what the universe looked like at 380,000 years old. And what it tells us is extraordinary. The early universe was almost perfectly smooth. The temperature of the microwave background varies across the sky by only about 1 part in 100,000, not 1%, not 1/10 of a percent, 1/10,000th of 1%. The universe started in a state of almost incomprehensible uniformity. Every galaxy, every cluster, every filament in the cosmic web grew from those tiny, tiny variations. Now, during the first 380,000 years, something was happening inside that plasma that would leave its mark on the universe for the rest of its existence. The plasma was not perfectly smooth. There were regions very slightly denser than average. Those regions exerted a slightly stronger gravitational pull. They started to accumulate more matter. But the plasma was hot, and hot plasma has pressure. That pressure pushed back against the gravitational collapse. The result was oscillation, a battle between gravity pulling matter inward and pressure pushing it outward. This created pressure waves moving through the plasma. Sound waves, in the most literal sense, but propagating through a medium of charged particles at a significant fraction of the speed of light. These waves had a characteristic size. They traveled at roughly 57% of the speed of light through the plasma, and they had about 380,000 years to travel before the transition happened. When the transition came, when the electrons joined the protons and the photons were freed, the plasma became transparent, and those sound waves froze, right where they were. The matter that had been oscillating locked into place. The preferred distance between overdense regions, the scale at which those frozen waves peaked, was about 490 million light-years. This scale is called the Baryon Acoustic Oscillation Scale, BAO for short. It is a ruler, baked into the cosmos at its very beginning, that astronomers can use to measure cosmic distances and test the standard model of cosmology. The physics made a clear prediction. Galaxies should be slightly more likely to be found at this specific separation from each other than at other separations. For decades, this remained a theoretical expectation, a beautiful result sitting in textbooks, waiting to be confirmed in observational data. Then, in 2005, astronomers working with the Sloan Digital Sky Survey announced they had found it. They had measured the positions of over 46,000 galaxies and found exactly the clustering signal the theory had predicted. The BAO scale was real, confirmed in data, and cosmologists breathed a collective sigh of relief, because this confirmation meant their model of the universe was fundamentally sound. The universe was homogeneous and isotropic, on large enough scales. It looked essentially the same in every direction, with no preferred location, no preferred direction. This principle is called the cosmological principle, and it is the bedrock of modern cosmology. And the Standard Model makes a specific prediction about how common structures of a given size should be. Large, coherent structures should be rare. The math said so. The simulations said so. Then came an observation that tested that prediction directly. The structure that will answer that question was identified through the analysis of X-ray galaxy cluster distributions. Galaxy clusters are among the most massive gravitationally bound structures in the known universe. At the center of these clusters, hundreds to thousands of galaxies move together within an enormous cloud of hot gas. That gas, heated to tens of millions of degrees by the gravitational energy of the cluster, emits powerfully in X-rays. It glows in a part of the electromagnetic spectrum invisible to the human eye, but perfectly detectable by space-based X-ray observatories. That X-ray emission is directly proportional to the depth of the gravitational potential the gas sits in, which means it traces mass. Not just the ordinary matter in stars and gas, but the total gravitational well, including the dark matter that dominates the cluster's mass budget. Galaxy clusters are therefore among the most reliable tracers of the large-scale matter distribution in the universe. Where clusters are more tightly concentrated than random placement would produce, there is an underlying excess of matter. The team worked with data from the CLASSIC survey, the Cosmic Large-Scale Structure in X-rays Cluster Survey, which draws on observations from the ROSAT All-Sky Survey to compile a statistically complete catalogue of galaxy clusters across the entire sky, applying clustering statistics to look for patterns in the distribution of those objects. The signal they found was significant. In a particular region of the sky, over a distance range of roughly 375 to 900 million light-years, galaxy clusters were concentrated in a way that implied a large-scale overdensity of matter. When they mapped that overdensity in 3 dimensions, using the redshift of each cluster to determine its distance, the structure that emerged had an extent of about 1.4 billion light-years in its longest dimension, and it had a shape, a branching, interconnected network of filaments and concentrations. The researchers named it after the quipu, the ancient Incan record-keeping device made of knotted cords. Each knot encoded information. The structure had a similar quality, a complex, branching topology rather than a simple blob or wall. They called it the quipu superstructure. The discovery was reported in 2025 by a team led by Hans Boehringer at the Max Planck Institute for Extraterrestrial Physics and their colleagues. The structure sits roughly 375 to 900 million light-years from Earth. At that distance, the light we use to observe it left the closest parts of the structure about 375 million years ago, while the light from its furthest edges left about 900 million years ago. Its estimated mass is about 240 quadrillion times the mass of the Sun. And it does not just test our sense of scale. It tests a foundational assumption about what the universe is allowed to look like at the very edge of where that assumption has been checked before. The cosmological principle is not just a convenient simplification. It is built into the mathematics of modern cosmology. The Standard Model of cosmology, called lambda CDM, or lambda cold dark matter, assumes that the universe is homogeneous and isotropic on large scales. Homogeneous means the same density everywhere, when averaged over large enough volumes. Isotropic means it looks the same in every direction. These assumptions allow cosmologists to write down the equations that describe the universe's expansion. They make the predictions about the cosmic microwave background work. They connect redshift measurements to actual distances, which is how we know how old the universe is, how fast it is expanding, and what it is made of. If the universe is not homogeneous on large scales, all of that becomes far more complicated. The scale at which the universe becomes homogeneous is expected to be somewhere around 200 to 300 million light-years. Above that scale, the universe should look essentially the same in every direction when averaged over large volumes. Individual structures should fade into the background noise of an even distribution. The Quipu superstructure is about 1.4 billion light-years across. That is roughly 5 to 7 times the scale at which homogeneity is supposed to take over. A structure that large, in a universe that is supposed to be smooth on much smaller scales, sits at the very edge of what the standard model allows. And the data confirms it is there. Before accepting that conclusion, it is important to understand exactly what cosmologists mean when they identify a structure like this. The Quipu is not a solid object. It is not a wall of rock or gas that you could navigate around. It is a statistical overdensity, a region where matter is slightly more concentrated than the cosmic average. The galaxy clusters that define it are separated from each other by hundreds of millions of light-years of mostly empty space. What they have in common is that they are more tightly concentrated than random placement would produce. This is the standard way large-scale structure is identified, not by drawing lines between individual objects, but by measuring whether a population of objects shows more clustering than random expectation. The same technique identified the BAO scale. It identified the cosmic web. It identified the Sloan Great Wall. It is a robust statistical approach refined over decades of research. The question for the Quipu is whether the signal truly indicates a single connected superstructure or whether it reflects a chance alignment of multiple independent concentrations at similar redshifts. This is a genuine challenge in large-scale structure research. When you map the three-dimensional distribution of galaxy clusters, you are working with data that has measurement uncertainties. Redshift measurements give distance estimates, but those estimates have error. Two clusters that appear close together in a reconstructed three-dimensional map might actually be more separated in depth. Their apparent proximity, partly an artifact of measurement uncertainty. Additionally, projection effects can create apparent connections. If several independent concentrations of clusters happen to lie in the same general direction on the sky, they can appear to form a continuous structure when they actually do not. Distinguishing a true connected superstructure from a projection of independent concentrations requires careful statistical analysis. The team behind the Quipu's discovery addressed this with multiple tests. They ran simulations to estimate how likely it would be to see a signal of that magnitude by chance in a universe following the standard model. They tested whether the structure remained statistically significant under different analysis parameters. They examined alternative explanations for the signal. Their conclusion was that the Quipu is a real large-scale overdensity. The scientific community subjected that conclusion to appropriate scrutiny. Some researchers expressed reservations about the methodology. Some pointed out that the signal, while real, might reflect a somewhat less coherent structure than the initial description suggested. The debate continues. But the current state of the evidence is that something genuinely remarkable is present in that region of the sky. Something that tests the standard model's predictions about the maximum scale of coherent, large-scale structure right at the edge of what those predictions allow. To understand why that test matters and is not just a curiosity, you need to understand the relationship between gravity and the expansion of the universe. Gravity is the engine of cosmic structure. Every galaxy, every cluster, every filament in the cosmic web formed because gravity pulled matter together over billions of years. But gravity has a competitor, the expansion of the universe. Space itself is expanding. Every galaxy is being carried away from every other galaxy by that expansion. And in the late 1990s, two independent teams of astronomers measuring the distances to distant supernovae discovered something that upended cosmology. The expansion of the universe is accelerating. Something is pushing the expansion faster and faster over time. That something is called dark energy. It is a property of space itself, an energy density inherent to the vacuum that produces an effective repulsive effect on cosmic scales. Dark energy makes up about 68% of the total energy content of the observable universe. Dark matter makes up about 27%. Normal matter, the kind that makes stars, planets, gas, clouds, and everything we can directly observe, makes up only about 5%. Everything visible is 5% of what is there. The other 95% is dark. Dark energy counteracts gravity on the largest scales. Below a certain scale, gravity dominates. Galaxies are bound together. Clusters hold together. Above that scale, dark energy wins. The accelerating expansion carries matter apart faster than gravity can pull it back. Structures cannot cohere at those scales because the expansion is too powerful. That scale is roughly comparable to the BAO scale, which is why the BAO scale represents an approximate ceiling on how large a coherent structure is expected to get. At one point, 4 billion light-years, the Quipu sits right at that ceiling. Simulations of the Standard Model do produce structures like this. They are just rare. And rare things are hard to find until you build a survey large and complete enough to catch one. That is precisely what the classic survey was designed to do. The history of how we came to map large-scale structure in the universe is the story of a series of revolutions, each driven by better instruments and bigger datasets. Edwin Hubble's work in the 1920s established that the universe extends far beyond the Milky Way. His observations of Cepheid variable stars, in what we then called the Andromeda Nebula, showed that it was not a small cloud of gas within our own galaxy, but a separate galaxy about 2.5 million light-years away. This instantly expanded the known scale of the universe by a factor of millions, and it set the stage for Hubble's subsequent discovery that most galaxies are moving away from us. The farther a galaxy is, the faster it recedes. This was the observational discovery of the expanding universe. All those galaxies moving apart from each other meant that in the past, everything had been closer together. Run the expansion backward, and you arrive at a state of extraordinary density and temperature, a beginning. For decades after Hubble, astronomers catalogued galaxies individually. They mapped their positions on the sky, measured their sizes and brightnesses, estimated their distances. But they were mostly working in 2 dimensions. The positions of galaxies on the celestial sphere, not the full 3-dimensional distribution. To get the 3rd dimension, you need distances. And for distant galaxies, the most practical distance measurement comes from redshift. By measuring how much a galaxy's light has been stretched to longer wavelengths by the expansion of the universe, you can calculate how far away it is. This technique, applied systematically to large numbers of galaxies, is what made three-dimensional mapping of the universe possible. The first serious redshift surveys began in the 1970s. They were small by modern standards. A few hundred galaxies, a few thousand. But even these small maps revealed something unexpected. Galaxies were not randomly distributed. They clustered. They formed chains and sheets. There were regions almost devoid of galaxies. The universe had large-scale structure. The CFA Redshift Survey, led by Margaret Geller and John Huckra at the Harvard-Smithsonian Center for Astrophysics, was one of the defining efforts of this era. Their 1989 paper announcing the CFA Great Wall showed the astronomy world a filament of galaxies stretching 500 million light-years. The image that accompanied the paper became one of the most iconic in modern cosmology. It looked like a figure with outstretched arms, what became known as the Stickman figure. And it showed unmistakably that the universe was organized on scales far larger than anyone had fully appreciated. The response from the theoretical community was mixed. Some embraced the discovery as confirmation of what computer simulations had been predicting. Others worried about systematic effects in the data that might make the structure look more dramatic than it truly was. Subsequent work, with larger samples and better statistics, confirmed the basic picture. The cosmic web is real. The structures are genuine. And they are large. Very large. But how large, exactly, was still being debated as the decade of the 1980s turned into the 1990s and then the 2000s. The Sloan Digital Sky Survey was the instrument that changed the conversation definitively. It began operations in 2000 and was designed specifically to map the three-dimensional distribution of galaxies and quasars across a significant fraction of the sky. The survey used a dedicated 2.5-meter telescope at Apache Point Observatory in New Mexico. Its wide-field camera imaged large areas of sky, detecting millions of galaxies and quasars. Its spectrograph could measure the redshifts of hundreds of objects simultaneously, using optical fibers to carry light from individual objects to the dispersing elements of the instrument. For each observation, a metal plate was drilled with holes at the positions of target objects in the field of view. Optical fibers were plugged into those holes. The other ends of the fibers fed into the spectrograph. When the telescope pointed at the field, the spectrograph spread each object's light into a spectrum. The spectrum revealed the redshift. Hundreds of redshifts in a single observation. Millions over the course of the full survey. The Sloan survey ultimately measured the redshifts of more than 3 million galaxies and quasars, building the largest three-dimensional map of the universe ever created. It confirmed the existence of the cosmic web with extraordinary statistical precision. It measured the BAO scale, finding the statistical excess of galaxy pairs at the predicted separation of about 490 million light-years. That confirmation of the BAO scale was one of the most important observational results in cosmology since the discovery of the cosmic microwave background itself. It meant the standard model was fundamentally correct about the origin of large-scale structure. The sound waves in the early plasma had left their imprint. The imprint was there. And the classic survey's X-ray cluster catalog, built from decades of satellite observations, provided the data that would eventually lead to the identification of the quipu. The specific analysis that identified the quipu used a technique called the Friends of Friends algorithm. This is a mathematical method for identifying clusters in a spatial point distribution. The basic idea is straightforward. Connect all pairs of objects within a chosen maximum separation. Some of those connections will form groups. Objects that are near each other join. Groups that are near other groups combine. If the linking length is calibrated correctly, the resulting connected groups correspond to physical overdensities in the matter distribution. The technique has been applied to identify galaxy clusters and superclusters in many different datasets. Applied to the classics cluster catalog, with a linking length calibrated to the local density of clusters, a connected structure emerged containing 68 galaxy clusters spread across a volume more than 1 billion light-years in its longest dimension. The statistical significance of that overdensity was assessed by comparing the observed clustering to a cosmological simulation called the Millennium Simulation, which models how structure grows under the Standard Model's assumptions. The comparison found something reassuring in one sense and remarkable in another. Structures of roughly this size and number are expected. The simulation predicted about 22 comparable superstructures in a volume of this size. The survey found 5. The Quipu is not a violation of the Standard Model. It is closer to the model's own prediction than it first appears. What makes it remarkable is not that it should not exist. It is that something this large, sitting this close to us, had never been mapped before. The scale of what we are discussing deserves to be stated clearly. The observable universe spans about 93 billion light-years in diameter. Within that volume, there are something like 2 trillion galaxies. Those galaxies are not randomly distributed. They are organized into the cosmic web, clusters at the densest nodes, filaments connecting the clusters, voids, vast regions of near emptiness, filling most of the volume. The filaments are typically hundreds of millions of light-years long. The voids can be several hundred million light-years across. The whole structure, on those scales, looks roughly the same in every direction. Homogeneous, as cosmologists say. If you average over large enough patches, the density is consistent. The scale at which this homogeneity sets in is somewhere around 200 to 300 million light-years. Above that scale, structure should smooth out. The universe should look featureless when averaged over large enough volumes. The Quipu superstructure is about 1.4 billion light-years in its longest dimension. That is roughly 5 to 7 times the scale at which homogeneity should take over. If the structure is what the analysis suggests, the universe is showing organized structure on scales where the Standard Model says it should be featureless. That is a real tension. Not necessarily a fatal problem for the model, but a real one. The model can accommodate rare, large structures. Any statistical model allows for outliers. The question is, how far outside the expected range this particular outlier sits? When cosmologists ran the numbers against the Millennium Simulation, the Quipu turned out to be consistent with what the model predicts. Not a violation. An expected rarity. Finally observed. And confirming a rare prediction is one of the quieter, less dramatic ways that science makes progress. There is something important to say about X-ray galaxy clusters that directly affects how we interpret the signal. Not all regions of the universe contain the same concentration of massive clusters. Galaxy clusters form where the underlying dark matter distribution is densest. The hot gas that fills the space between a cluster's galaxies, heated to tens of millions of degrees by gravitational compression, emits X-rays, whose brightness scales with the depth of the gravitational well. That makes X-ray luminosity a direct measure of cluster mass, and cluster mass a direct tracer of the underlying matter distribution. The chain of inference is tight. More X-ray luminous clusters indicates deeper gravitational wells, which indicates greater total mass concentration, including dark matter. The Quipu sits at a distance corresponding to a look-back time of only about 600 million years. That is recent, in cosmic terms, which is part of what makes it so remarkable. The universe we are seeing when we observe it is not so different from the universe we live in today. And the fact that X-ray cluster concentration in the Quipu region shows a statistical overdensity suggests that the underlying matter distribution in that region is genuinely unusual. The X-ray excess in the Quipu region is therefore a direct tracer of a matter excess. The chain of inference is more direct here than with many other large-scale structure probes. Hot intracluster gas emits X-rays in proportion to the depth of the gravitational potential it sits in, which traces the underlying mass, including dark matter. That chain has uncertainties at every link. But across the statistical power of the full cluster sample, the overall argument is robust enough that the scientific community takes the structure seriously. Even those who debate its exact nature agree something unusual is there. Alongside the Quipu, there is another candidate for the largest structure in the universe, and understanding the comparison reveals something important about how science handles claims at its frontiers. The Hercules, Corona, Borealis Great Wall was first reported in 2013. It was identified through the distribution of gamma-ray bursts. Gamma-ray bursts are the most energetic explosive events in the known universe. When a very massive star reaches the end of its life and its core collapses, the resulting explosion can release more energy in a few seconds than the Sun will emit over its entire 10 billion year lifetime. These events are detectable across the entire observable universe. The Swift satellite and other gamma-ray observatories have catalogued thousands of them. The analysis of their distribution on the sky suggested that gamma-ray bursts in a particular region of the sky were clustering together. The inferred scale of the structure was somewhere between 6 and 10 billion light-years. If confirmed, that would make it vastly larger than the Quipu. But the evidence has been controversial. Gamma-ray bursts are a much smaller population than the X-ray galaxy clusters used to identify the Quipu. Smaller samples make statistical claims harder to confirm. There are also concerns about systematic effect. The detection of gamma-ray bursts depends heavily on which part of the sky the observing satellites were pointing at the time. If certain regions of the sky were observed more frequently, you would find more gamma-ray bursts there, regardless of whether more actually occur there. This kind of pointing bias is difficult to eliminate completely from the analysis. Different research teams, applying different statistical methods to the same data, have reached different conclusions about whether the structure is real. The Quipu, by contrast, was identified using a much larger sample of well-characterized objects, with a methodology that has been validated across many other applications. That does not make the Quipu's interpretation certain, but it is a more credible foundation. And the fact that we are seriously debating structures of these scales tells you something about how far our ability to map the universe has come in just a few decades. Another structure is relevant to this story, and it approaches the picture from the opposite direction. Not an overdensity of matter, but an underdensity. The Eridanus supervoid. If the Quipu is a region where matter is more concentrated than average, the Eridanus supervoid is the opposite. It is roughly 1.8 billion light-years across, centered in the direction of the constellation Eridanus in the southern sky, where the density of galaxies drops significantly below the cosmic average. The Eridanus supervoid matters here for a specific reason. In the cosmic microwave background, there is an anomalous region called the cold spot, a patch of sky where the temperature of the microwave background is slightly cooler than its surroundings. The temperature difference is small, only about 70 microkelvin below the average. But the cold spot's combination of size and depth makes it statistically unusual. The Eridanus supervoid appears to line up with the cold spot. There is a physical mechanism that would link the two. When photons from the cosmic microwave background travel through a void, they have to pass through a region of below-average gravitational potential. In a universe with constant dark energy, photons entering a void lose energy going in and gain it back, climbing out, with no net change. But in a universe where dark energy causes the expansion to accelerate, the void itself gets shallower while the photon is inside it. The expanding universe has stretched the void. The photon climbs out of a slightly shallower well than the one it climbed into. It emerges very slightly cooler than it entered. This is called the integrated Sachs-Wolf effect. If the Eridanus supervoid is responsible for the cold spot, the void would need to be deeper and larger than the standard model easily accommodates. Taken together, the Quipu and the Eridanus supervoid suggest that the universe has extremes at the largest scales, both overdense and underdense, that sit at the edges of what the model predicts is plausible. They may be part of a broader pattern. If the cosmic web has more pronounced contrast between its densest filaments and deepest voids than the standard model predicts, both anomalies would be explained by the same underlying cause, a universe with slightly more large-scale structure than expected. That is a testable proposition, and it is being tested. Dark matter is the dominant player in this story, and it deserves careful attention. About 85% of all the matter in the universe is dark. It does not emit light. It does not absorb light. It does not interact electromagnetically at all. The only way we know it exists is through its gravitational effect. It bends light from distant objects, a phenomenon called gravitational lensing. It holds galaxies together against the centrifugal forces of rotation that should, without extra mass, fling the outer stars into space. Galaxies rotate, but the outer regions rotate faster than the visible mass alone could sustain. There must be additional mass. Dark matter provides it. Dark matter also forms enormous halos around galaxies, extending far beyond the visible stars and gas. The Milky Way's dark matter halo extends hundreds of thousands of light-years beyond the visible disk, and dark matter forms the invisible scaffolding of the cosmic web. The filaments of the web are primarily dark matter filaments. Normal matter falls into those filaments, concentrating where dark matter is densest, forming the galaxies and clusters we can see. The voids of the cosmic web are regions where dark matter is sparse. What we observe in galaxy surveys is normal matter tracing the dark matter distribution. For the Quipu to exist, the dark matter distribution in that region of the universe had to be organized on extraordinary scales. The initial density fluctuations in the early universe had to have placed enough excess dark matter in that region that billions of years of gravitational evolution amplified it into the overdensity, reflected in today's cluster distribution. Whether the initial conditions allow for that depends on the details of inflation. The theory of inflation proposes that the universe underwent an extraordinarily rapid expansion in the first tiny fraction of a second after the Big Bang, far faster than any expansion since. During that expansion, quantum fluctuations, the random noise of quantum mechanics, were stretched from microscopic scales to cosmic scales. Those stretched fluctuations became the initial density variations that gravity later amplified into the cosmic web. The specific distribution of those initial fluctuations depends on what drove inflation. The simplest models predict a nearly scale-invariant spectrum, meaning roughly equal amounts of variation on every scale. If inflation produced slightly more large-scale variation than the simplest models predict, that would provide more seeds for large-scale structure. More seeds for structures like the quipu. This is directly testable with better measurements of the cosmic microwave background. Next-generation experiments will measure the temperature and polarization of that background with precision far exceeding what current instruments achieve. If the initial conditions were unusual in the way needed to explain the quipu, those experiments will detect the signature. If the initial conditions match the simplest inflation models exactly, then the quipu sits at the very edge of what those conditions can produce, which is consistent with what the comparison to simulations already found. We have not yet directly detected a dark matter particle. This is one of the central unsolved problems in modern physics. We are extremely confident dark matter exists. The evidence from galaxy rotation curves, from gravitational lensing, from the structure of the cosmic web, from the power spectrum of the cosmic microwave background, all of it requires dark matter. But we do not know what dark matter is made of. The most popular theoretical candidate for decades was the weakly interacting massive particle, or WIMP. WIMPs were appealing because they arose naturally in theoretical extensions of the standard model of particle physics, particularly in a framework called supersymmetry. They had predicted masses in the range of 10 to 1,000 times the mass of a proton, and they would interact with ordinary matter through the weak nuclear force, very rarely, but occasionally. That occasional interaction was what ground-based detectors were built to catch. Experiments, built deep underground, shielded from cosmic ray backgrounds, using ultra-pure crystals or tanks of liquid noble gases as detection media, have searched for the signal of a dark matter particle, knocking a nucleus slightly out of place. The sensitivity of these experiments has improved by many orders of magnitude over the past 2 decades. And still, no confirmed detection. This does not mean dark matter particles do not exist. It means that if they do, their interaction with ordinary matter is weaker than the most favorable predictions suggested, or their mass is outside the ranges being searched, or they have properties that differ from simple assumptions. The null results have pushed physicists to broaden their search. Axions, originally proposed to solve a problem in particle physics unrelated to cosmology, have become serious dark matter candidates. Primordial black holes, formed directly from density fluctuations in the early universe, have received renewed attention. Sterile neutrinos, particles that mix with ordinary neutrinos but have no standard model interactions beyond gravity, are another possibility. Each candidate predicts different behavior at cosmic scales. Different candidates produce different distributions of dark matter on small and large scales. Different candidates would contribute differently to the formation of structures like the quipu. Even though the quipu matches standard predictions, its existence still constrains the dark matter parameter space. Because matching a rare prediction, this precisely rules out models that would have made it too common or too rare. The nature of dark matter and the statistics of rare large structures like the quipu are connected questions. Better answers to one sharpen the other. The next generation of surveys will test these questions directly. The Dark Energy Spectroscopic Instrument, DESI, began its primary survey in 2021. It is mounted on the Male 4-meter telescope at Kitt Peak National Observatory in Arizona. Its key capability is the simultaneous measurement of 5,000 spectra per observation. 5,000 individual robotic fiber positioners reconfigure themselves automatically between observations. Within minutes of finishing one field, the robots reposition all 5,000 fibers to new targets in the next field. This automation allows the survey to operate with extraordinary efficiency. Over its 5-year primary mission, DESI will measure redshifts for about 40 million galaxies and quasars. More than 10 times the total of the entire Sloan Digital Sky Survey accumulated over 20 years. The 3-dimensional map it produces will cover more than a third of the sky and extend to high redshifts, probing the universe when it was only a fraction of its current age. Within that map, the statistical detection of structures, like the quipu, can be repeated at far higher confidence. First results from DESI have already been remarkable. Early data releases confirmed the BAO measurement with high precision, and they found subtle hints of tension with the standard lambda CDM model in how structure has grown over cosmic time. Whether those hints solidify into a statistically significant deviation or dissolve with more data is one of the central questions of the next few years. The Euclid mission, launched by the European Space Agency in 2023, operates from a gravitationally stable location about 930,000 miles from Earth. From there, it images the sky free from atmospheric distortions. Its goal is to map the shapes and distances of about 1.5 billion galaxies across a third of the sky. Euclid's measurements of galaxy shapes, distorted by the gravitational lensing of intervening matter, will reconstruct the distribution of all matter, dark and visible, between us and those distant galaxies. This is a direct probe of large-scale structure, not a statistical inference from where galaxies cluster, a direct map of where the matter is. If the quipu has a corresponding dark matter overdensity, Euclid's lensing maps could reveal it directly. That would transform the quipu from a statistical signal in X-ray cluster data to a directly imaged feature of the full matter distribution. Much harder to explain as a statistical artifact. The Vera C. Rubin Observatory in Chile, completing commissioning, will conduct the Legacy Survey of Space and Time, a 10-year imaging survey of the southern sky. Every few nights, the observatory's camera will image the entire accessible southern sky. Over 10 years, each patch of sky will be imaged roughly 1,000 times. The accumulated data will discover millions of supernovae, map dark matter through gravitational lensing of billions of galaxies, and document the large-scale structure of the southern universe in unprecedented detail. These 3 instruments together represent a qualitative leap in our ability to map the cosmos and test cosmological models. The data being collected now will refine what we know about structures like the quipu. Whether it is truly a one-in-several event, exactly as rare as the model predicts, or whether better statistics reveal that superstructures like it are slightly more common than current simulations suggest. Either answer is valuable. Either answer sharpens the model further. The philosophical dimension of the quipu's discovery deserves attention. Not in the vague sense of marveling at scale, but in the more specific sense of what it means to be the kind of creatures that can find something like this. The structure is roughly 600 million light-years away, on average. The light we use to observe it left those galaxy clusters only about 600 million years ago. In cosmic terms, we are seeing something almost contemporary, something whose large-scale shape has not changed dramatically in the time the light has taken to reach us. The quipu exists right now, in very nearly the form we observe. Its galaxy clusters are still there, still massive, still filled with the hot gas that traces their gravitational depth. The galaxies within those clusters have continued to age and evolve. The large-scale filaments of the quipu have continued to evolve under gravity and the accelerating expansion. We know what it looked like 600 million years ago. And 600 million years, in a 13.8 billion-year-old universe, is close enough to today that the structure we see is essentially the one that exists now. This is one of the genuinely strange aspects of observational cosmology. We can see the past clearly. We cannot see the present at any distance, not for any object more than a few light seconds from Earth. The sun you see is the sun as it was 8 minutes ago. The nearest star is more than 4 years in the past. The nearest large galaxy is 2.5 million years in the past. And the quipu is about 600 million years in the past. Every deep sky image is a window not into the universe as it is, but into the universe as it was. The deeper you look, the further back you see. The universe's entire history is spread out in space around us. And what we see at the distance of the quipu is a universe already organizing itself into structures that push the limits of what theory says it should be capable of. That has been the pattern. At every scale we have probed, the universe has been more organized, more structured, more extreme than simple first guesses predicted. Not because the physics is wrong, but because the universe uses the physics it has, gravity, pressure, quantum noise, dark matter, dark energy, to the fullest extent that physics allows. It builds the largest structures possible under its own rules. And occasionally, it builds something that makes us question whether we have understood the rules correctly. There is a broader pattern of anomalies in cosmology that the quipu is part of. Not contradictions of the standard model, not clear-cut falsifications, but tensions, uncomfortable deviations at the edges of the model's predictions. The Hubble tension is the most widely discussed. The Hubble constant is the rate at which the universe is expanding. It can be measured 2 ways. One way is to analyze the cosmic microwave background and use the standard model to predict what the expansion rate should be today. The other is to measure distances directly to nearby galaxies using objects whose intrinsic brightness is known, and calculate the expansion rate from how fast those objects are receding. The 2 methods give different answers. Not by a tiny amount, by enough that the discrepancy is now statistically very significant. Multiple independent teams using multiple independent methods have confirmed it. The standard model does not naturally explain it. Some researchers argue it points to new physics in the early universe. Others suggest that dark energy might change over time rather than being a constant property of space. Others argue the distance measurements might carry systematic errors not yet identified. Nobody has a definitive answer. There is also the sigma-8 tension. Sigma-8 is a measure of how clumped the matter in the universe is on a specific scale. The standard model predicts a particular level of clumpiness based on the early universe measurements. Direct observations of the distribution of matter in the current universe suggest slightly less clumping than predicted. Again, the discrepancy is real. Again, nobody knows exactly what causes it. And then, there are the large-scale structure anomalies. The cold spot in the microwave background and the Eridanus supervoid it corresponds to are among the clearest examples, a void deeper and larger than the standard model comfortably predicts. The Quipu, interestingly, is not one of these anomalies. It turned out to match expectations closely. But its discovery is part of the same broader effort. The push to map the largest scales precisely enough to know which features are genuine tension and which are simply rare events the model already allows for. None of the confirmed anomalies, individually, breaks the standard model. But collectively, they suggest that the model, which is extraordinarily successful over an enormous range of phenomena, may still be missing something at the largest scales. And large scales are exactly where we have the fewest data points, the most difficulty eliminating systematic effects, and the most sensitivity to whatever dark energy actually is. If dark energy is not simply a constant, if it has some dynamics, some evolution over time, the effects would be most visible at the largest scales. At the scales where the Quipu sits. That is why these anomalies, taken together, are taken seriously. Not because any single one demands a revolution, but because the pattern they form suggests that the frontier is close. It is worth understanding where the frontier in large-scale structure currently sits. The observations we can make are limited by several factors. The size of surveys, the depth they reach, the accuracy of the methods used to measure distances, the ability to separate true structure from statistical noise and systematic effects. Each generation of surveys has pushed these limits further. And each time the limits have been pushed, larger structures have been revealed. The question of whether there is a fundamental maximum scale beyond which no coherent structure exists has been tested repeatedly. And repeatedly, the answer has been that the maximum is larger than previously thought. This could mean the maximum genuinely scales with the survey size, meaning every survey finds structures nearly as large as the survey itself allows. That would suggest the universe is organized on all scales we can probe, with no true smoothness scale. Or it could mean we are genuinely converging on a maximum scale that exists for physical reasons, with each generation of surveys finding structures approaching, but not quite exceeding that maximum. The BAO scale provides a strong theoretical argument for why the maximum should exist and where it should be. The Quipu sits right at that maximum, and the comparison to simulations already places it inside the allowed range, if only barely. The precision of that placement depends on the statistical assumptions used to define the boundary. Deci, Euclid, and Rubin will sharpen that boundary with unprecedented precision. A more exact answer for exactly how comfortably the Quipu fits is coming. Let us think about what has to happen inside a structure like the Quipu. It is not just matter sitting there. It is matter in motion. Galaxies within the Quipu's filaments are all falling toward the denser regions, pulled by the collective gravity of the overdensity. Some are moving at hundreds of miles per second relative to the local average. Some galaxies within the Quipu's most concentrated nodes are colliding with each other. These collisions are not the high-speed impacts of everyday experience. When galaxies merge, the stars themselves almost never collide directly, because the stars are so small compared to the distances between them. Even in the densest galaxy cluster, the nearest stars to any given star are typically trillions of miles away. When two galaxies pass through each other during a merger, the stars sail past each other. What collides is the gas. The vast clouds of hydrogen and dust that fill the space between stars are compressed and heated as the two galaxies interact. The resulting shocks trigger waves of star formation. New stars burst into existence across the merging system. Many of those new stars are massive and short-lived, burning through their fuel in just a few million years and ending in supernovae. Those supernovae enrich the surrounding gas with heavy elements forged in the star's cores. The gas feeding the central black holes of the merging galaxies intensifies, driving quasar activity. And at the same time, the tidal forces of the interaction distort the shapes of both galaxies. Spiral arms are stretched into long tidal tails of stars. The orderly structure of disk galaxies is disrupted. Over hundreds of millions of years, the two galaxies settle into a single merged system, typically an elliptical galaxy, with its stars moving in complex orbits that retain the memory of the merger in their dynamics. This is happening, on some scale, throughout the Quipu. In its densest regions, galaxy mergers are more frequent than in typical regions of the universe. That is part of why the X-ray signal is strong there. The excess galaxy density drives excess galaxy interactions, which drives excess cluster formation and X-ray emission. The whole cycle is gravitationally driven, self-reinforcing, playing out over timescales of hundreds of millions to billions of years. The Quipu is not a static structure. It is a process. An ongoing gravitational evolution that has been running for billions of years and will continue for billions more. We see a snapshot of it, as it appeared several 100 million years ago. The universe began, as far as we can determine, in a state of extraordinary simplicity. Not simplicity in the sense of being easy to understand, but simplicity in the sense of being described by relatively few numbers. The density of normal matter. The density of dark matter. The density of dark energy. The initial power spectrum of density fluctuations. The Hubble constant. A handful of other parameters. From those few numbers, plugged into the equations of general relativity and particle physics, you can calculate the history of the universe. You can predict the abundance of helium formed in the first few minutes. You can calculate the temperature of the cosmic microwave background. You can determine when the first stars formed. You can model the growth of the cosmic web. You can estimate the distribution of galaxy masses today. All of this from a handful of numbers. The remarkable thing is that it works. The predictions match the observations to within a few percent across an extraordinary range of phenomena. And the Quipu tested that at one of the most demanding scales available. It passed, which is its own kind of remarkable. A model built from a handful of numbers correctly anticipated the existence of the largest structure ever mapped before anyone had mapped it. Every major advance in cosmology in the past century came from observations that did not fit the prevailing model. The discovery of the expanding universe. The discovery of the cosmic microwave background. The discovery of dark matter in galaxy rotation curves. The discovery of the accelerating expansion. Each of those observations was initially puzzling, even uncomfortable. Each forced a revision of the theoretical framework. Each led to a deeper understanding. The Quipu is a different kind of discovery. It did not force a revision. It confirmed one of the model's own quiet predictions, one that had been sitting unverified for years simply because no survey had been complete enough to test it. That is still doing what the best astronomical discoveries do. It is closing one question and opening several others about measurement, about mass, about what else is still out there, waiting to be mapped. Every structure in this story was assembled from the same initial ingredients: the quantum fluctuations of the Big Bang, dark matter, normal matter, gravity, time. Those ingredients, operating without any plan or purpose, produced everything from the first hydrogen atoms to the largest structure ever documented. The range of scales they cover is extraordinary. From the size of an atomic nucleus to the scale of the Quipu spans more than 40 orders of magnitude, 40 powers of 10. The same force, gravity, with the same constant strength, with the same mathematical description, operates across every one of those scales. No switch flips at large scales. No new physics takes over. Just gravity. Persistent, building structure wherever it can, for as long as it can, against the opposition of dark energy and the expansion of space. The Quipu is gravity's work at its largest known scale, the biggest thing it has managed to assemble. In a universe that is 13.8 billion years old and 93 billion light-years across. 1.4 billion light-years of organized matter, assembled from quantum noise, predicted by theory, found by patient observation. The Sloan Digital Sky Survey did not simply produce data. It produced a revolution in how astronomers think about large-scale structure. Before the survey, the cosmic web was known to exist, but its statistical properties, the sizes of voids, the lengths of filaments, the masses of clusters, were all measured with large uncertainties. The survey changed that. For the first time, cosmologists had a sample large enough and well characterized enough to measure the statistical properties of the cosmic web with precision. They could compare those properties to predictions from computer simulations. They could identify where the simulations matched and where they fell short. And the simulations, run on the world's most powerful supercomputers, became the primary tool for testing cosmological models. These simulations are remarkable achievements. They start with the conditions of the early universe, a nearly uniform distribution of matter with tiny fluctuations, and evolve it forward in time under the laws of gravity and fluid dynamics. The Millennium simulation, completed in 2005, was the first simulation large enough to reliably reproduce the large-scale structure of the universe. It tracked more than 10 billion particles of dark matter across a cubic volume over 2 billion light-years on a side. At the time, it was the largest cosmological simulation ever run. The output was extraordinary. The simulation produced a virtual universe that looked, statistically, almost exactly like the real one. Filaments, voids, clusters, all emerged naturally from the initial conditions. No special tuning, no adjustable parameters beyond the standard model's initial values, just gravity and time. The illustrious simulation, completed in 2014, added gas physics and star formation to the dark matter dynamics. It tracked the evolution of stars, gas, black holes, and dark matter simultaneously, allowing it to model not just the distribution of matter, but the properties of individual galaxies. The resulting virtual galaxies had morphologies, colors, and star formation histories remarkably similar to observed galaxies. Elliptical galaxies formed where mergers had disrupted the disk structure. Spiral galaxies formed where the accretion of gas into rotating disks had been orderly. The match between simulations and observations is one of the strongest pieces of evidence that the standard model of cosmology is fundamentally correct. And it is against this baseline that the Quipu was tested. Researchers took the same volume of the Millennium simulation ran the identical cluster-finding method and asked a simple question: how many structures this size should exist in a volume this large? The simulation's answer was about 22. The survey of the real sky found 5, including the quipu. That is close enough to be called agreement within the uncertainty of a small sample. The standard model was not broken by this discovery. It was tested at one of its most difficult edges, and it held. That is not a disappointing result. Confirming a rare prediction is exactly what a healthy theory is supposed to do when pushed to its limits. The history of cosmology is, in large part, the history of discovering that the universe is larger than previously thought. In the early 20th century, astronomers debated whether the Milky Way was the entire universe or just one of many comparable structures. The Great Debate of 1920 was a formal public confrontation between Harlow Shapley, who believed the Milky Way encompassed the entire universe, and Heber Curtis, who believed the spiral nebulae were separate galaxies far beyond the Milky Way. Shapley was partly right. He had correctly measured the scale of the Milky Way and placed the Sun far from its center, overturning earlier assumptions. But he was wrong about the nebulae. Curtis was right that they were external galaxies. Hubble settled the debate in the mid-1920s with his measurements of Cepheid variables in Andromeda. And with that settlement came a staggering expansion of the known universe. Not just Andromeda. Every spiral nebula was a separate galaxy. Hundreds of millions of galaxies, each containing hundreds of billions of stars. The universe was unimaginably larger than anyone had imagined just years before. Then came the discovery of the expanding universe. Then, the cosmic microwave background. Then, the cosmic web. Then, dark matter and dark energy. At every step, the universe turned out to be larger, more complex, and more organized than the previous picture had accommodated. The quipu fits this pattern. It is another step in a long sequence of discoveries that have pushed the known extent and organization of the universe beyond what any prior generation thought possible. The question is whether it is a step within the existing framework or a step that requires a new one. The evidence so far suggests it is on the boundary. And that is exactly where the most interesting science happens. It is worth taking a moment to think about the instruments that built the foundation for discoveries like the quipu, because they represent decades of engineering and technological development. The Sloan Digital Sky Surveys telescope was built specifically for survey work. Unlike the great telescopes of earlier eras, which were designed for studying individual objects in detail, the Sloan telescope was optimized for covering as much sky as quickly as possible. Its primary mirror is 2.5 meters in diameter. That is modest by the standards of modern research telescopes. Some contemporary instruments have mirrors 10 to 30 times larger in area. But the Sloan telescope has an exceptionally wide field of view. It can image a patch of sky about 3 degrees across in a single pointing. For comparison, the full moon is about half a degree across. The Sloan telescope can image a patch of sky 36 times the area of the full moon in a single image. That wide field, combined with a camera containing 30 separate detectors arranged in a mosaic, allowed it to image the sky with extraordinary efficiency. The spectrograph that measured the millions of redshifts was equally carefully designed. The fiber optic system that carried light from individual galaxies to the spectrograph had to maintain the alignment of hundreds of fibers precisely enough that the light from each target hit the right detector. The gratings and prisms that dispersed the light into spectra had to produce clean, well-calibrated spectra that software could analyze reliably. The entire chain, from photons leaving a distant galaxy 600 million light-years away to a redshift value stored in a database, had to work flawlessly at every step, and it did for millions of objects. The software pipeline that processed the raw images into calibrated spectra and then into measured redshifts was one of the largest and most complex astronomical software systems ever built. It had to handle the quirks of the camera, correct for the varying transparency of the atmosphere, subtract the background light of the sky, extract the spectrum of each target from the raw detector data, measure the positions of spectral lines, and calculate a redshift, all automatically, for millions of objects, without human review of each step. The algorithms behind that pipeline were developed over years of work by dozens of people, and they worked reliably enough to produce the datasets that built the statistical foundation modern cosmology runs on. Discoveries like the Quipu are made possible by engineering, by software, by calibration, by the unglamorous work of making instruments that function reliably across millions of individual measurements. That context matters. Great discoveries do not come from inspiration alone. They come from the patient construction of the tools and methods needed to make the next observation possible. The question of what the universe looks like on the very largest scales approaching and exceeding the Quipu's extent, is one that the next generation of surveys will address directly. The dark energy spectroscopic instrument will not just revisit the Quipu's region, it will map the universe's structure across a much larger volume than the Sloan survey covered. It will build a three-dimensional map of galaxies and quasars that will reveal not just individual structures, but the statistical distribution of structure sizes. That distribution is a precise prediction of the standard model. If the model is correct, the distribution of structure sizes should follow a specific mathematical form. Large structures should be rare, but not impossibly rare. If DESI finds the distribution matches the predictions, the Quipu is an outlier within the model. If DESI finds the distribution has more large structures than expected, something is missing from the model. That kind of precision test was not possible with the Sloan survey data. With 40 million objects instead of 3 million, the statistical power to distinguish these possibilities will be far greater. Euclid will add an independent measurement through weak gravitational lensing. Lensing surveys measure the total matter distribution, dark and visible, without relying on galaxies as tracers. They directly measure the gravitational potential everywhere in the survey volume. If the Quipu has a corresponding dark matter overdensity, Euclid will find it. If the region has the same dark matter density as surrounding areas, despite the cluster overdensity, that would require a different explanation. Perhaps the cluster concentration in that region was shaped by something other than simple excess matter density. Perhaps the region has an unusual history of galaxy mergers due to its large-scale geometry rather than its density. These are specific hypotheses that specific measurements can test. The era of vague anomalies, where something seems unusual but cannot be precisely characterized, is ending for the Quipu. Within this decade, the structure's nature will be known with much greater confidence. There is one aspect of studying structures at the Quipu's scale that is genuinely different from studying smaller cosmic structures. The universe is not static. It is evolving. And when you look at an object 600 million light-years away, you are seeing it as it was 600 million years ago. 600 million years is not trivial. But in a universe that is 13.8 billion years old, it is a small fraction of the total. The universe, at that moment, was already mature. Its large-scale structure was already well developed. The cosmic web was already close to its present form. The quipu we observe is therefore not some distant fossil from a radically different era. It is a snapshot of a structure that, in cosmic terms, looks much like what it looks like today. That is actually one of the things that makes it so significant. We are not inferring the quipu from ancient light that tells us what the universe once was. We are looking at something that exists, in very nearly its present form, right now. The light showing us the quipu's present state left those galaxy clusters only about 600 million years ago. It is already arriving. Its galaxy clusters are still there, still massive, still hot with X-ray emitting gas. The structure we see is not a fossil. It is a living feature of the present-day cosmos. And that makes it stranger in one sense, not less strange. Something this large exists around us, right now, and we only just found it. There is something about all of this that connects back to the most basic question. Why is there structure at all? Why did the universe not simply remain a perfectly uniform gas, expanding and cooling toward emptiness? The answer is quantum mechanics. In the very early universe, before inflation, the distribution of matter was subject to quantum uncertainty. Quantum mechanics does not allow perfect uniformity. It imposes fundamental limits on how precisely position and density can be specified simultaneously. Even a perfectly uniform initial state would be subject to quantum fluctuations, tiny random variations that are an inescapable feature of nature at the quantum scale. Inflation took those microscopic quantum fluctuations and stretched them to cosmic scales. It turned the quantum noise of the early universe into the density variations that gravity later amplified into the cosmic web. This is one of the most profound connections in all of science. The largest structures in the universe, the cosmic web, the galaxy clusters, the superclusters, the quipu, all owe their existence to quantum mechanical uncertainty, to the fundamental randomness at the heart of physics. If quantum mechanics were different, if the uncertainty principle was slightly different, the fluctuations would have been different. The cosmic web would have a different character. Structures like the quipu might not exist, or might be much more or much less common. The connection between the quantum scale and the cosmic scale, mediated by inflation, is one of the deepest insights of modern cosmology. And it makes the quipu something more than a very large collection of galaxies. It makes it a macroscopic consequence of quantum physics. A frozen accident of the quantum noise of the Big Bang, stretched across more than 1 billion light-years. The quipu is the largest structure anyone has ever documented, but it is not the most distant structure. It is not the most massive structure, and it is not the most visually striking structure. Those distinctions go to other things. The most distant structures we can probe with current technology are in the cosmic microwave background itself, the afterglow of the Big Bang, which dates from about 380,000 years after the beginning. That is as far back as electromagnetic radiation can show us. For earlier times, we would need to observe gravitational waves or neutrinos, which escape the dense early universe more easily than photons. The next generation of gravitational wave detectors, far more sensitive than the current LIGO and Virgo instruments, might eventually detect gravitational waves from the very early universe. Those would be the most ancient cosmic signals ever recorded. the most massive structures are not filaments or superclusters. They are galaxy clusters. The Coma cluster, one of the nearest large clusters to us, contains thousands of galaxies and has a total mass of several 100 trillion times the mass of the Sun. Much of that mass is in hot X-ray emitting gas that fills the space between the cluster's galaxies. The Bullet cluster, famous as one of the most direct pieces of evidence for dark matter, contains two galaxy clusters that have passed through each other. The hot gas from the two clusters, which interacts electromagnetically and slows down during the collision, has been separated from the dark matter, which passes through without interaction. Gravitational lensing maps show the dark matter halos on either side of the central gas concentration. The visible separation is one of the clearest demonstrations of dark matter's properties. None of these clusters rivals the Quipu in extent, but they are more massive per unit volume. The Quipu's overdensity is spread thin across an enormous volume. The most visually striking structures are galaxies themselves. The spiral galaxies, with their sweeping arms of stars and dust, are among the most beautiful objects in the observable universe. The Andromeda Galaxy, visible to the naked eye in the northern hemisphere, spans about 220,000 light-years and contains roughly 1 trillion stars. It is close enough that individual stars can be resolved with large telescopes. Its structure is visible in extraordinary detail. Nothing about the Quipu is visually striking in that way. You cannot see it with any telescope. You can only infer it from the pattern of dots on a redshift map. And yet, it is the largest structure ever found. Beauty and size are not the same thing in cosmology. The most profound objects are not always the most visually dramatic. Now, we come to the question that any discussion of the Quipu must address. What does it mean? Not in a mystical sense, in a practical, scientific sense. What does the existence of the Quipu tell us about the universe? The comparison to simulations gave a clear answer. The Quipu is not a violation of the standard model. It is a rare event the model already predicted, observed for the first time because a survey finally became complete enough to catch it. That is valuable in its own right. It means the model's behavior at the extremes of its statistical range has been tested and not falsified. Every test the model survives strengthens our confidence in it. But being expected does not make the Quipu unimportant. A structure this size, sitting this close to us, has real consequences for how we measure the universe. Every large-scale survey assumes that the volume it samples is representative of the cosmos as a whole. A structure like the Quipu breaks that assumption locally. It pulls on everything around it. Galaxies near it stream toward it under its gravity, and that streaming motion gets mixed into any measurement of cosmic expansion made in its direction. Astronomers have long known that the local group itself is moving relative to the cosmic microwave background at a few hundred miles per second, pulled by something large in the surrounding volume. Superstructures like the Quipu, Shapley, and their neighbors are the leading candidates for that pull. To get a clean measurement of how fast the universe is truly expanding, you need to know where the nearby superstructures are and how strongly they are tugging on everything nearby. Before this survey, that map did not exist in complete form. Now it does. The universe will not stop surprising us. That is a prediction one can make with considerable confidence. Not because of mysticism, but because of history. Every generation of astronomers has discovered things that exceeded the imaginative reach of the previous generation. Every new instrument has found things that existing models struggled to accommodate. And every accommodation, every refinement, and revision of the models has led to a deeper understanding. The cosmic web was not imagined before it was found. The BAO scale was not obvious from the data until the surveys became large enough to detect it. Dark energy was not predicted to exist before the supernova observations forced cosmologists to accept it. And the largest known structure in the universe was sitting in the data for years before anyone had the tools and the sample size to pull the signal out and name it. Whatever comes next will follow the same pattern. The anomalies that currently sit at the edges of the standard model will either be explained within the model as more precise data arrives, or they will accumulate into something that demands a new framework. Either way, the universe will be better understood. And somewhere in that better understanding, the Quipu will have played a role. As the structure that tested the model at one of its hardest edges, as the structure that showed a rare prediction could be found, given a survey complete enough to catch it. As the largest thing we have ever found, sitting right at the edge of what physics says should be common, 1.4 billion light-years, found in data, named for knotted strings, matching the model that describes everything else. The universe, it turns out, is not shy about building the largest structures it can. And we, it turns out, are not shy about looking for them. So the next time you stand outside and look up at a clear sky, you are looking through a thin slice of the local universe, past nearby stars, past the band of the Milky Way, toward galaxies hundreds of millions of light years away. And behind all of that, in a particular direction, roughly 600 million light-years distant, there is a knotted web of matter spanning more than 1 billion light-years, assembled from the quantum noise of the Big Bang, shaped by dark matter, traced by the X-ray glow of galaxy clusters in its densest regions, studied by astronomers who spent careers analyzing millions of spectra, named by researchers who saw in its branching complexity the knotted strings of an ancient recording device, and now known, imperfectly but genuinely, as the largest structure in the observable universe. The universe has built many things. Stars that live for trillions of years. Black holes that contain the mass of billions of suns. Galaxies that span hundreds of thousands of light years, filaments that stretch for hundreds of millions, and this, 1.4 billion light years of organized matter, the largest known structure in the universe. Found by patient, methodical observation, tested against theory and matched, still being refined, and waiting patiently for the next generation of instruments to sharpen the picture further. There is one more dimension to this story that has not yet been addressed, and it concerns the relationship between what we find in the universe and what we are capable of finding. Astronomy is limited by what instruments can detect. It is also limited by the theoretical frameworks that tell us what to look for. Before the cosmic web was predicted by theory, nobody organized surveys around finding it. Before the BAO scale was calculated, nobody designed surveys around measuring it. The discovery of the Quipu followed a specific scientific question. Are there structures in the X-ray cluster distribution that exceed the expected clustering scale? That question could only be asked once the theoretical predictions were clear enough and the dataset large enough to test them. Both conditions were met by the 2020s, once the classic survey reached the completeness needed for an all-sky search. And so, the question was asked. and the answer came back reassuring, in a way that was still genuinely surprising. This is how science works at its frontier. Not by stumbling onto discoveries blindly, but by having precise enough predictions that deviations from them are detectable. The standard model of cosmology makes precise predictions. The Quipu is a test of those predictions. And the first round of that test has already returned a result. The current comparison to simulations says the model works, that the Quipu is a rare but fully allowable outlier. That is not the end of the story. Every measurement carries uncertainty, and the precision of that comparison will only improve as better data arrives. The next round might simply sharpen the same conclusion, or it might reveal something the first comparison was not sensitive enough to catch. Either way, the refinement will come from the same patient, methodical process that found the Quipu in the first place. Data, analysis, comparison, better data, better analysis, a clearer picture. There is a specific prediction the standard model makes that directly bears on the Quipu's interpretation: the matter-power spectrum. This is the distribution of how much structure exists at each scale, how much mass is concentrated in galaxy-sized fluctuations, how much in cluster-sized fluctuations, how much in supercluster-sized fluctuations. The standard model predicts a specific shape for this spectrum: more power at smaller scales, less at larger scales, falling off in a way set by the initial conditions and the subsequent evolution of structure under gravity. The BAO scale appears as a feature in this spectrum, a slight bump at the scale corresponding to the frozen sound waves. Above the BAO scale, the spectrum should fall off steeply. Structures much larger than the BAO scale should contain very little excess power. A structure as large as the Quipu would represent excess power at a scale where the model predicts very little. Measuring the matter-power spectrum at scales comparable to the Quipu is exactly what DESI and Euclid are designed to do. DESI's millions of redshifts will constrain the power spectrum with unprecedented precision across a range of scales. If the power spectrum at large scales is higher than the standard model predicts, that is direct evidence that something is missing from the model. It would mean the initial density fluctuations from inflation had more power at large scales than the simplest inflation models produce, or that dark energy or gravity behaves differently than assumed at the largest scales, or that some systematic effect in the measurements has given the false appearance of excess large-scale power. Distinguishing between these possibilities requires multiple independent measurement methods. That is exactly what the combination of DESI spectroscopy and Euclid lensing provides. Two independent methods. One based on galaxy positions. One based on the gravitational distortion of shapes. If both point to the same large-scale power excess, that is strong evidence of something real. If they disagree, there is probably a systematic effect in one or both methods. Either outcome teaches us something. The history of cosmology also holds cautionary tales about claiming too much from individual anomalies. In 1986, astronomers John Huchra and Margaret Geller were conducting the CFA redshift survey. While mapping the distribution of galaxies in a thin slice of the sky, they noticed what appeared to be a remarkable structure: a thin, sharply defined filament of galaxies curving across their map. They called it the Great Wall, the CFA Great Wall. It became one of the most discussed structures in cosmology for years. But subsequent analysis, with better data and larger survey volumes, showed that the Great Wall was not as sharply defined or as singularly special as the initial discovery suggested. It was real, but it was part of a larger, more complex web of structure. The sharpness of its appearance in the original map was partly an artifact of the thin slice through which the survey had looked. A structure that appears as a distinct wall in one plane might appear as an ordinary filament when viewed from a different angle. This does not mean the CFA Great Wall was a mistake. It means that first impressions of large-scale structures are often refined by subsequent work. The same principle applies to the Quipu. Its initial characterization, as reported in 2025, represents a first look. A first look with good data and careful analysis, but a first look. Subsequent analysis will refine the picture. The structure's true extent, its coherence, its statistical significance will all be better characterized with more data. That refinement might make the Quipu more impressive than the initial description. Or it might reveal that some part of the initial characterization was inflated by limited coverage or by statistical uncertainties. Science treats first results with appropriate skepticism, especially for extraordinary claims. The Quipu deserves that treatment. Not dismissal, but skepticism, in the productive sense of the word, the kind that leads to better experiments. There is a concept in cosmology called cosmic variance that is relevant to understanding the Quipu. Cosmic variance refers to the fundamental statistical limitation imposed by the fact that we observe only one universe. For any statistical measurement, more samples means smaller uncertainty. If you want to know the average height of people in a city, you get a better estimate by measuring 1,000 people than by measuring 10. In cosmology, the universe is our sample. We have one universe. We cannot measure another. For measurements of the very largest scales, approaching the size of the observable universe, the number of independent regions we can sample is small. There might be only a few dozen regions of the universe large enough to contain a structure like the Quipu. That means our statistical uncertainty about how common such structures are is inherently large. Even if the standard model is exactly right, and the probability of finding a structure this large is small, we cannot use our single observation of one structure to definitively say the probability is wrong. We need to find either many such structures or none. Finding exactly one, which is our current situation, leaves both possibilities open. More survey coverage. Finding more structures like the Quipu, or confirming their absence, is the only way to reduce cosmic variance. DESI's larger survey volume will provide more independent regions to search. If DESI finds several comparable structures, that is strong evidence that the standard model underestimates their abundance. If DESI finds the Quipu is unique among the regions it surveys, that is consistent with the model's prediction of rarity. Cosmic variance is a fundamental challenge for all large-scale structure cosmology. But it is one that can be reduced, if not eliminated, by surveying larger volumes. That is what the next generation of instruments will do. The universe has no obligation to confine itself to our most elegant theoretical descriptions. The standard model of cosmology is elegant. It starts from simple principles, quantum fluctuations inflated to cosmic scales, gravity amplifying those fluctuations over billions of years, dark matter providing the dominant scaffolding, dark energy driving the accelerating expansion, and derives an extraordinarily rich and complex universe from those simple starting points. The model works beautifully for almost everything we have measured. The cosmic microwave background, the abundance of light elements from Big Bang nucleosynthesis, the large-scale distribution of galaxies, the BAO scale, the expansion history of the universe. All of these are explained by the same framework. That is remarkable. But the universe was not designed to be elegant. It was not optimized for our theoretical convenience. If the initial conditions of the Big Bang included more large-scale power than the simplest inflation models produce, the universe would have more large-scale structure. Not because anyone planned it that way, but because that is what those initial conditions, plus billions of years of gravity, would produce. The question of whether the quipu represents such excess is ultimately a question about what actually happened in the earliest moments of the universe's existence. It is a question about the inflationary epoch, about the specific quantum field that drove inflation, about the spectrum of fluctuations that quantum field produced. These are questions that the cosmic microwave background, measured with increasing precision, can address. The polarization patterns in the microwave background carry information about the initial conditions that cannot be extracted from temperature alone. Specifically, they carry information about the amplitude and spectral index of the initial power spectrum at different scales. If inflation produced excess large-scale power, that excess would leave a signature in the polarization that experiments like the Simons Observatory and CMB Stage 4 can measure. Those experiments are coming. The connection between the largest structure in the universe and the quantum mechanics of the inflationary epoch is direct and measurable. That connection is one of the things that makes large-scale structure cosmology so powerful. The structure of this story has brought us from the familiar, the question of how the universe is organized, through the technical, the BAO scale, and the statistics of X-ray cluster distributions, to the profound, the limits of the standard model, and what the quipu implies about the initial conditions of the universe. That journey is itself a reflection of how modern cosmology works. It starts with observation. Something appears in the data. It does not match simple expectations. The question becomes, is the discrepancy real, or is it an artifact of limited data or imperfect methods? If real, the next question is, how significant is it? Can the existing theoretical framework accommodate it with reasonable parameter adjustments? Or does it require something fundamentally new? And the only way to answer those questions is with more and better data, more observations, more precise measurements, larger surveys, independent methods, better simulations. That is the cycle. And the quipu is currently in the middle of it. The initial discovery has been made. The significance of the discovery has been established to the degree that current data allows. The implications for the standard model have been analyzed. And the next round of observations is underway, aimed at resolving the ambiguities that remain. This is science in progress, not a finished story. A story being written now, with the ending still unknown. What we do know, with confidence, is that the universe is organized on scales that exceed any prior expectation. What we know is that the standard model of cosmology, for all its remarkable success, has now been tested at one of its most difficult limits by a structure like the quipu, and it held. What we know is that the next generation of instruments will sharpen that result, refining exactly how comfortably rare structures like this one fit within the far tails of the model's statistical predictions. What we know is that somewhere, roughly 375 to 900 million light-years away in the direction of a particular patch of sky, there is a superstructure spanning more than 1 billion light-years, made of dark matter and normal matter, traced by the X-ray light of galaxy clusters in its densest concentrations. Named for an ancient recording device, found in a catalogue of X-ray cluster observations, and now part of the ongoing conversation about what the universe actually is and how it came to be this way. The Quipu is the largest thing we have ever found. But the universe is not done building things, and we are not done looking. Let us return to something that sits at the heart of this entire discussion: the cosmological principle. The idea that the universe looks the same everywhere and in every direction on large enough scales. It is worth understanding why cosmologists believe this so strongly, and why a structure like the Quipu, sitting right at its edge, was worth checking so carefully. The cosmological principle is not just assumed. It is observed. When astronomers survey the sky in different directions, they find the same types of galaxies in roughly the same densities. When they measure the temperature of the cosmic microwave background in different directions, they find it uniform to 1 part in 100,000. When they count galaxies in different regions of the sky, averaging over volumes large enough to wash out local structure, they find consistent densities. The evidence for large-scale homogeneity is strong, but it is not infinitely strong. Every measurement has a scale on which it is made. The cosmological principle has been tested well on scales up to several 100 million light-years. On larger scales, the tests become harder. The samples are smaller. The statistics are weaker. The systematic effects are harder to control. The Quipu is at the scale where the tests are hardest, where the evidence for the cosmological principle is weakest. That is not a coincidence. Large-scale structure anomalies always appear at the largest scales being probed. The question is always whether the anomaly is a sign of genuine physics at those scales or an artifact of the limited statistics available at the frontier of measurement. With the BAO scale confirmed and the cosmological principle well established at several 100 million light-years, the question of what happens at 1 billion light-years is the next natural test. And that test is now underway. There is something worth noting about the naming of the structure. Quipu, an ancient Incan device made of knotted strings used to record information. The choice of name reflects something about the way scientists think. When you find something genuinely new, something that has no prior name because it has never been observed before, the name you give it says something about how you are conceptualizing it. The researchers who named the Quipu saw in its branching, interconnected network of filaments and nodes the same topology as the knotted strings. Multiple strands, connections, knots at the intersections. The structure is not a single thing. It is a complex, a network. The name captures that quality better than a simple geometric label like Great Wall or filament. It also connects modern cosmology to ancient human creativity. The Quipu, as a device, was used by the Incan civilization for centuries to record information about agriculture, population, and tribute. It encoded data in a physical, tangible form. The Quipu superstructure encodes the history of the universe's density fluctuations in a physical, spatial form. The knotted strings of the ancient device and the knotted filaments of the cosmic superstructure are different things, but they share the quality of encoding information in their topology, in the arrangement of their connections. That is not a trivial parallel. The cosmic web is, in a real sense, a record of the universe's history, a record written in the positions of galaxies, a record that astronomers read with redshift surveys and statistical analysis. And the Quipu is the largest chapter of that record that anyone has yet decoded. The discovery of the Quipu is one small step in a much longer scientific journey. The journey to understand the origin, structure, and fate of the universe. It is a journey that has been underway for a century in its modern form, and for millennia in the broader sense of humans trying to understand the cosmos. Every generation has added to what is known. Every generation has discovered that what is known is smaller than what is unknown. That pattern shows no sign of changing. The universe is genuinely vast, and genuinely complex, and genuinely stranger than our intuitions suggest it should be. The Quipu is one example of that strangeness, a structure that sits right at the edge of what the model allows and matches it anyway. A structure that tests the best model physics has produced for describing the cosmos and holds up. A structure that still demands better observations and better analysis, if only to sharpen exactly how well it fits. That is not a burden. It is what a well-tested theory gives back once you finally have the tools to check it. A question that matters. A question that, when answered, will tell us something new and true about the universe. The Quipu has given cosmology that question. The next decade of observations will provide the answer. And when it comes, it will be one more step in the oldest human enterprise, trying to understand where we are, what this is, how it got here, and what it all means. We are far from finished, but we are much further than we were, and that is enough reason to keep looking. The universe began with a whisper, a quantum fluctuation so small that no instrument we have could detect it directly. That whisper was stretched by inflation to cosmic scales. It seeded the density variations that gravity spent billions of years amplifying. It produced the cosmic web, the galaxies, the clusters, the filaments, the superclusters, and it produced the Quipu, the largest known structure in the observable universe. A whisper from the beginning, written in the positions of galaxies across more than 1 billion light-years of space. We can read that whisper. Not perfectly, not yet completely, but we can read it. And what it tells us about the universe is still being deciphered. The instruments are running. The data is accumulating. The analysis continues. And somewhere in all of it, the universe is waiting to tell us whether the Quipu is the limit of what gravity can build, or just the largest thing we have found so far. That answer is coming. Before the surveys and satellite observatories that found the Quipu existed, before the X-ray detectors and the sky surveys and the cluster catalogs, someone had to believe the data was worth collecting. Someone had to make the case that mapping millions of galaxies across billions of light years was scientifically valuable. That argument was not obvious at the time. Major observatories and funding agencies do not commit decades of telescope time and hundreds of millions of dollars to projects without compelling scientific justification. The scientists who proposed the Sloan Digital Sky Survey had to articulate clearly and convincingly why a three-dimensional map of the universe at that scale would tell us something we could not learn any other way. Their arguments centered on precision cosmology, on the ability to test the standard model's predictions with enough statistical power to detect deviations at the few percent level. On the measurement of the Bow scale, which could serve as a standard ruler for measuring the universe's expansion history. On the characterization of large-scale structure, which would constrain the properties of dark matter and dark energy. Those arguments were persuasive. The survey was built. It ran. It succeeded, beyond what its designers anticipated in some ways. And along the way, it produced the data that helped establish the statistical baseline against which structures like the Quipu would later be measured. Not because anyone planned to find the Quipu, but because each comprehensive dataset makes the next discovery possible. That is one of the most reliable patterns in the history of science. Large, comprehensive datasets reveal things no one was looking for. The Quipu was one of those things. And whatever Desi and Euclid and Rubin reveal will include things nobody is looking for either. Things that will be surprising or uncomfortable, or that do not fit the current model. Things that will generate debates, prompt new analyses, and eventually lead to better understanding. That process, from data to discovery to debate to understanding, is the engine of cosmology. The Quipu is one turn of that engine, and the engine keeps running. So we end with this. The observable universe is about 93 billion light-years across. It contains about 2 trillion galaxies. Those galaxies are organized into a cosmic web of filaments and voids. And in one particular corner of that web, at a distance of roughly 600 million light-years, there is a structure spanning more than 1 billion light-years, the largest known structure in the universe, found in a catalogue of X-ray galaxy clusters, named for an ancient Incan knotted string device, matching the theory that describes the rest of the cosmos at the very edge of what that theory allows. Still being measured. We found it. We named it. We are still learning exactly what it changes. That is where we are, and that is exactly where we should be, at the frontier, asking the next question, building the next instrument, looking further, finding more. Good night.